Today we're going to study about latent heat. So up until now we've seen how an energy transfer between a system and its surroundings can yield a temperature change. Now if energy is added to a certain or subtracted to a certain system, that's not always the case that there will be a change in temperature. In certain cases, the temperature will remain constant, and this happens when we have a phase change, meaning that the physical characteristics of that substance change, and we have either melting or solidification or vaporization or condensation. So basically what happens is that the internal energy still changes, but the temperature remains constant. This happens, for instance, if we take vaporization. This is because the physical distance between the molecules increases, since the bonds between the molecules of the liquid break, and the physical distance between molecules increases, and with that the intermolecular potential energy also increases. So now we're going to define something that's called a higher phase material. So this is the material that's in its higher phase, meaning that it has a higher internal energy value. For instance, if we take a cube of ice and a cup of water, the water is a higher phase material since it has more internal energy. The same if we take water and let's say steam. Steam is a higher energy, contains more energy, and as a result is a higher phase material. Now we're going to see the formula for latent heat. Now the latent heat, since we don't have a temperature change, depends on the amount of substance or the mass of the substance. Now latent heat is defined as the energy needed to change the phase of a certain mass of substance. So Q, being the heat, is equal to L, the latent heat, times the change in mass. Now this change in mass is the change in higher phase, is the change in mass of the higher phase material. For instance, if we have water and ice at equilibrium, meaning the temperature is at 0 degrees Celsius. In this case, if we add a certain amount of heat to the ice, and then let's say the initial mass of the ice is Mi, or the initial mass of the water, and Mf is the final mass of the water. So basically, when we add heat to that system, the ice will begin to melt, and if we add enough heat, then all of the ice will melt, and in that case the change in mass of the water or the higher phase material will be the final minus the initial. Okay, now let's move to something different. Now the latent heat value, for instance, for vaporization will be equal to the same as condensation, but remember that the sign will be different. So basically when we have melting or vaporization, we have a plus sign for the heat, since we're adding heat to the system and we're raising the internal energy. But we have a minus if we have solidification or freezing, or if you have condensation, since you're losing heat in order to decrease the internal energy of the system. Now the latent heat of vaporization is equal to the latent heat of condensation, and the latent heat of melting is the same as the latent heat of solidification. Now here I have a graph, and we have a let's say we have a mass, a certain amount of ice, and that ice is at first at minus 30 degrees Celsius. Now on the y-axis I have the temperature here in degrees Celsius, and on the x-axis I have the energy added in joules. Now we're going to go step by step. So first of all, the ice is at minus 30 degrees Celsius. So here we're starting to add energy to the ice by heat, and we're raising the temperature of the ice to 0 degrees Celsius. So meaning we have a temperature change, and here we can calculate this if we can know the specific heat of the ice. So the energy that will be needed for the ice will be the mass of the ice times the specific heat of the ice times the change in temperature, so which will be 30 degrees Celsius. Now then, from 0 degrees Celsius we have the melting of the ice. So here we have a phase change, so we don't have a temperature change, and we're adding heat to that system. And here we can see that we have ice and water, since here ice and water are in equilibrium, and we're converting ice into water. And we can see that to raise the temperature of the ice from minus 30 to 0 degrees Celsius, we only need 62.7 degrees Celsius. But if you want to raise the temperature or if you want to melt the ice, then we need a lot more energy. Then from 0 degrees Celsius we're taking the water to 100 degrees, and also we can calculate that using this, and we know that the specific heat of water is 4186 joules per kilogram times degrees Celsius. Then we have another phase change. This time we have vaporization. So we have the water at 100 degrees Celsius, and we're adding heat. And as you can see, we don't have a temperature change since the temperature is constant. Here, water is converted into steam. So we have water and steam in equilibrium, and this process continues until all the water is converted into steam. Then we're raising the temperature of the steam from 90 to 120 degrees Celsius. And as you can see, this is a big energy delta, so meaning that we need a lot more energy to convert the water at 100 degrees Celsius into steam. Then we need to convert ice of 0 degrees Celsius into water. Last thing that I want to mention is that since steam at 100 degrees Celsius has much more energy than water at 100 degrees Celsius, if our skin comes in contact with steam at 100 degrees Celsius, then that's much more painful, since first we have to wait that the steam is converted, is condensed into water, and then that the skin will absorb the temperature of the water, will absorb the energy coming from the water, then the temperature of the water will drop. But if we have a water droplet on our skin that's at 100 degrees Celsius, then the skin can immediately start to take away energy from the water droplet, and the water will lose energy, and its temperature will decrease. In the next video, we're going to solve one or two problems using latent heat, and then we're going to continue on in our journey about the first law of thermodynamics.